think we'll go ahead and get started here. So that is our team. The ugly guy right here, that is me. That's the one presenting. So this is actually in our shop in New Sharon, Iowa. And there's some of our SLA machines there in the background. This is Dan, the owner. He is the founder, and he started the company in 2011 as a support and service for stereolithography equipment. So we support a lot of legacy equipment, older machines that maybe the manufacturer doesn't want to support anymore. We still will, so we'll take care of that if you guys have anything like that that you would need. Also in 2016, we started RP Sales, and that is where we are selling the stereolithography equipment as well as Rise and desktop metal. So if you have any questions about any of the technologies that we offer, please feel free to reach out to us. So this is actually our shop. It's on Dan's farm. It's out in the middle of nowhere, but it's a gorgeous facility, completely temperature and humidity controlled. It's a great place to spend a little bit of time, and we like to take our time, have fun, and do some things. This is actually a fishing pond out behind Dan's house. This is the owner's house right here. So pull some pretty nice sized fish out of there every once in a while. Okay, so let's talk about this project. I started this in conjunction with Marshall Miller. He's the committee chair for hard tooling from AFS. And he asked us to compare FDM or FFF style printing to SL and what stereolithography can do for hard tooling for sand patterns. We partnered with Trident Alloys out of Massachusetts. They do an average of 6,000 castings a year. And William Kuby, Ethan Seward, and Donnie Galaska are kind of the pieces of the puzzle at Trident Alloys. And Donnie was the pattern maker, so he's got some specific comments in here as well. The stereolithography part was printed on Unitech equipment at our shop. And we did this on, I believe it was a 450. And then we also, the FFF part was printed at the Georgia Technical Center for FlowServe in Rock Springs, Georgia. So this is a smaller part of a larger grant that was done through AFS for AM hard tooling and process benchmarking. The goal is to help adopt 3D printing for hard tooling as it pertains to sand printing or sand casting. And the goal is to make the patterns 50% faster and 50% cheaper than the conventional wood patterns. So we are comparing the cost of hard tooling for sand, for patterns for sand casting with stereolithography. And we're doing that on a 450, and then the FFF part was printed on a Stacker 2. So for anyone who's maybe not as familiar with the process, that's what the pattern looked like. And you mount that to a board inside of a box, or the board then gets slid into a box. And you see the gray parts there, the little gray circles, those are actually plugs that get put in to the part after it's screwed to the board. So that's basically Bondo, and then they smooth it over to make it seamless in the pattern. So that's what it looks like. Then you start adding sand, and you start packing sand around the pattern. You completely fill it up. And then lastly, you remove the pattern and from that, or on that board, and then that's what you're left with is the half of the pattern. So you would do this for 2 halves, bring the 2 halves of the pattern together, and then there's gating and some lost my the word I was looking for, where you pour the metal in. Those are some areas that are not represented in this particular pattern. Okay, the points of comparison for this particular project are we were looking for part quality and smoothness, strength and durability, the print and post-processing time, as well as overall cost. So this is not the pattern, but that's the closest pattern I could find to a wood pattern. And this is just a traditional method of how they used to do this, or how they still do this in a lot of environments. The material is typically maple. There's about $250 worth of material. The time to create this is about 24 hours. So that's literally 3 full days in a pattern maker working on that to get the part accurate and to what they need to use for. The hourly cost is about $100 an hour. That's kind of across the board number that we've used. So that brings this particular pattern in at about $2,650. Now, that's going to be durable and it's going to last a long time, but it spends most of its life sitting on a shelf in case they need to do it again. So if you're not familiar with how FFF or FDM works, filament is on a spool. It gets pushed into a hot end and then laid down layer by layer. And here is the part being printed on the stacker. So it's a stacker 2. The material is I-beam PLA. That's a blue color. You can see the part there. The material cost. So a 2 kilogram spool of this I-beam PLA is about $89. The print time for this particular part was about 37 hours. It has a volume of 1.06 kg, and the total cost in material only to print that is $46.97. So I'm not incorporating any machine utilization time into or cost into my numbers. It's only the material and the time it takes to actually accomplish the print. So here it is, actually mounted to a board, and then this is the board that's going to have the box around it and then packed with sand. And you can see the screw holes there where they mounted the pattern to the board. They've been filled in with Bondo. So post-processing, again, we used a $100 per hour cost. The time to sand the part to the required smoothness took about a full day. And this isn't even that complicated of a part. If we look at it again, you can see there's the layer lines there and how they've been knocked down by the sanding process. That actually was about 9 hours of total post-process time. The part was mounted to the board, and there were some re-drilling required for the holes. They weren't printed at the correct size, so the pattern maker had to spend a little bit of time reaming those out and getting that mounted to the board correctly. So total post-processing costs of about $900. So stereolithography. If you're not familiar with how stereolithography works, just like the FDM, it starts with a CAD drawing. It gets put into a slice software, and then from there it gets transferred over to the SLA machine, and a laser is going to shoot into a mirroring or a scanning system, and that laser is then reflected into the vat of resin, layer by layer, creating the part. There is our part. That's actually on the bed of the printer. And we used our Union Tech Pilot 450. We use Somos Evolve for the material. If you have any questions about that material, we have lots of information on that. So the material cost for this particular material is $278 per kilogram. And the time to print was about a little less than 20 hours. Total volume, 1.21 kg, and for a total print cost of $336.38. So on the surface, that part does seem much more expensive from a printing process. There is our part mounted to the platform. And the post-processing looks like this, again, $100 an hour. The time required to clean the part and UV cure it was only about 35 minutes. So from removing the part from the platform of the printer, removing the supports, washing off the excess resin, and curing it was a total of 35 minutes. So it's really not that much time. Same amount of time was required to do any excess drilling and mounting to the board. For a total post-process time of about 1 hour and 1.58 hours, with a total cost of $150.34. So that's kind of the breakdown there. You're starting to see some real discrepancies there between the post-processing of the FDM part compared to the SL part. So this was the pattern maker reaction. The FF tool is much lighter in weight, seemed fragile. You can feel the layer lines of the pattern, especially if you rub your fingernail across it. Anybody who's ever picked up FDM parts is familiar with what that would be like. Had a tough time working with the plastic, especially drilling through the part. What's meant there is when he was reaming out the holes, there's a wall thickness or in the holes or around the entire part itself. And the hole was small enough that in the process of drilling, it actually exposed the internal structure of the part. So that's what he's referring to by a tough time working with the part there. The SL tool, first touch was wow. It feels much heavier, it's much more durable, and it's certainly smoother. And it has the same problems when we were drilling out that part. This part we did with a 5 mil wall thickness, so the shell was about 5 mil, and same issues when drilling into the part. It exposed that internal structure on the inside, which we use Tetrashell from Material Magics to do that, to maintain that internal strength. So, okay, the SL part was far superior to the FFF part. We'd like to see more heftiness to the plastic parts when screwing to the board because the plastic gives more than wood would give. It doesn't seat to the board as well as you would have liked. Several of those things can be taken care of both on the FFF and the SL side simply by making that wall thickness thicker. We are actually in the process of working on another sample that we're going to do an 8 mil wall thickness. So that's going to give us a lot more dense of a part and also strengthen it up a little bit. So when it screws down, it's going to seat better to the board. Also, because we removed a lot of the wall thickness inside that hole, that caused a little bit of expansion in the plastic as it's being cinched down to the board as well. So again, correct size holes and maybe a little bit more thickness to the shell, and we'd have a much better robust part. Okay, so into some of the final pricing here. The FFF part, $46.97 plus the $900 in post-processing for a total cost of $946.97. The SL part, $336.38 plus the $158.34 for a total of $494.72, giving them the stereolithography part an actual cost savings of $452.25. That kind of surprised me. I really wasn't expecting that. So we would make sure that is accounted for. Next, the justification side here for the Unitech. So what I did was I took the cost of both printers and I subtracted one from the other. So the stacker cost $8,000. Unitech Pilot is $125,000. So we have an average part print savings of about $500. Again, I took some general liberties here to try and make the numbers nice and clean, just from a ballpark. This part wasn't that big. It's really about 14 inches across is all the bigger it was. So $117,000 is the difference in the price of the machines. So if you were going to split that across parts, $500 each, 234 parts. If you amortize that out over 2 years, you would need to do 9.75 parts per month to justify a stereolithography printer for this type of an application. Now, we got to remember that is only half of a casting because there's 2 halves to the casting. So that really number could be just under 5 parts per month. So if you're going to do 5 full parts per month, in 2 years, you can completely pay off the machine in a price difference in the savings that you're going to acquire. I also ran this on a little bit smaller of a printer. The 250 cost only $89.8. So if we do the same type of calculation, we're looking at 130 or 164 parts over 2 years. You're looking at just over 3.5 parts total per month to be able to justify that. So pretty big difference there when you start looking at that. How overall people think SL might be a little bit more expensive, which in some cases it is. If we're looking at cost comparison between the stereolithography printer and maybe like a Stratasys 450 printer, we're actually cheaper now. So if you're looking at that type of equipment, the justification is going to look even better. So some few conclusions here. Stereolithography has seen a bit of a rebirth. Material scientists have completely caught up to what the stereolithography process can do. Because of this, SL is getting new chances to fill manufacturing spaces that had previously been abandoned because the materials were really thought to be too weak or brittle. That is still a very common misconception about stereolithography. In the 80s and 90s, yes, the material was brittle and it did not have a great longevity of parts. They would definitely yellow over time, just a matter of days or weeks, depending on the environment. And the material sciences have really made a difference here in the last, especially 5 years, but in the 15 years before that, a lot of advances came along as well. The cost of open source material printers like UniTech is coming down, so allowing for new opportunities in prototyping and manufacturing. And in this case, I think hard tooling for castings is a great opportunity to expand and look at that as an option as well. I think it's also important to point out again that UniTech printers are open source for materials, so you're not locked into a specific material vendor. You do not buy materials from UniTech. We partner with DSM Somos, and you can use their materials, but there's other materials that are being developed all the time, and that is an important piece of the puzzle. When these new materials come out, our printers will be able to print with them. And we as a company, RP America, we work with those materials, we set up the parameters on those materials so the end customer doesn't have to go through that learning process. We kind of do all that for you. So that's another thing that RP America brings to the table.